Next, we have to move symmetric relation. We have to show symmetric relation. The definition: a relation R is said to be symmetric if A is related to B. If A is related to B, which implies B is related to A. That is, A comma B is belongs to R, or otherwise B comma A is belongs to R. For example, let L be the set of line in the plane. So L cross L is equal to the Li minus Lj. That is, Li comma Lj is belongs to L. In this way, we have to prove the symmetric relation. Next, we see the transitive relation. R is said to be transitive if and only if A related to B and B is related to C, which implies A is related to C. That is, the order pair A comma B is belongs to R and B comma C is belongs to R, which implies the order pair A comma C is belongs to R. For example, I be the set of integers I cross I equal to A comma B. Let R equal to A comma B. Next, we have to see the definition equivalence relation. The relation R is defined from A to B. The relation R is defined from A to B is said to be equivalence if it is satisfying reflective and symmetric and transitive. The R is said to be equivalence relation if it is satisfying reflexive, symmetric, transitive. R is satisfying three relations. For example, I be a set of integers. Then I cross I, which is equal to A comma B. A comma B belongs to integers I. R is relation. Let R equal to A comma B, order pair A comma B, such that A comma B belongs to I. A less than B is the multiple of fixed integer n. So R is relation defined on I. Verify R is equivalence relation defined on I. This is the problem. Let R equal to order pair A comma B. So A less than B is the multiple of A comma B is the multiple of fixed integer n. So we have to prove R is relation. It would be equivalence relation. So first, let us taking A comma A, two element in capital I, set of integers. So A minus B is equal to A minus A equal to 0. Multiples of n is the multiples of n. So A relation A is related to A. R is reflective. Then next we have to prove R is symmetric. So A comma B is two integer in set of integer I. Suppose that A is relation to B means A minus B is the multiples of n. So B minus A is also a multiples of n. So B is related to A. Therefore R is symmetric. We have to prove next. We have to prove A, B, C belongs to integer set of integer I. Suppose that a is related to b and b is related to c. I have to prove a is related to c. So a minus b and b minus c are the multiples of n. A minus b and b minus c are multiples of n. A minus b is the multiple of n. So a is related to c. Therefore r is reflective. Hence the above relation R is the equivalence relation.